Thank you for joining us today. I'm here to talk about Facebook and how to do well in their coding interviews. My name is Gail Lockton-McDowell, and my background is a software engineer. I worked for a while at Google, also a bit at Microsoft and Apple, did a lot of work at Google on the hiring committee, doing interviews, especially for software engineers. And then I wrote Crack It in Coding Interview, which I'm sure many of you guys already have. It's the major book that programmers get for interview prep. And then I also do work to help coach people through interviews, and as well as do work on the other side and help companies on their hiring process. So I'm sure it came as a bit of a surprise to you guys that Facebook is prepping people for interviews. That seems really counterintuitive. A lot of times when I tell people I do this, people are like, well, wait, why does Facebook do this? That seems kind of weird. So the reason why is essentially Facebook wants you to do well. They want you to be prepared. They want you to be comfortable. They don't want you to struggle because you didn't know what to expect, because you didn't get the chance to learn the things you need to learn. So the reason why I'm telling you this is so that you understand that not only am I obviously on your side, I really want you to do well, but your recruiter and your interviewers genuinely want you to do well. They genuinely want you to do your best. And that means that if you have questions, you can ask your recruiter, you can ask your interviewer. Your recruiter isn't trying to surprise you with how many interviews you're going to get, how long the process takes, what kinds of things interviewers might want to ask. So feel free to ask your recruiter any follow-up questions, but also know that in the interview itself, your interviewer is there as a resource. And I'll talk about some specific examples later on. But your interviewer is there. You can ask them things like, do you want me to start coding yet or not? So know that you don't have to guess what the process and expectations are. People are there to help you along the way. So with that, I also want to add that if you want to get a copy of these slides or look at them as you watch through the video, you can get them at gail.com, which is my website. Click on events and then search for Facebook on the page. There's also an auto response you can use. If you send me an email at g@gail.com with the subject FB Prep, one word, you'll get a link to the slides, a handout that I'll talk about later on, and a few other resources. So with that, I'm going to jump into the interview side. So first, what to expect. I always hesitate to say this exact, get into these specifics, because some people will read this and think, this is exactly what my process will be. And that's not what I mean. So let me just put that disclaimer out there that this is a typical process. It's not every single person has this exact process. And again, you can always ask your recruiter what to expect if you're not already told. So as far as the number of interviews, kind of general schedule, things like that, what you should expect is first interview will generally be on the phone. You'll have, it'll often be kind of a coding and algorithms interview, along with some questions about your background and some other things. When you come on site, very typically, people will have 2 algorithm and coding interviews that focus primarily on that, 1 design interview, and then 1 interview that's kind of a mix of behavioral questions and some algorithms and coding. But again, this is just typical. People with particular backgrounds might have more or less. Someone currently in college might not have any design. Someone who has much more experience or real specialty might have a bit more focus on design. So yes, this is what a typical person goes through, but it's not every single person. Feel free to ask your recruiter what you should expect. In a given interview, like say a coding interview, what you'll generally see is a bit of chit-chat at the beginning about your prior experience, questions on your resume, things like that. A bit at the end where you get to ask the interviewer about the company, the role, things like that. And then the middle of it will be technical questions, at least for a coding interview. Typically, interviewers tend to ask 2 questions, but this is not at all universal. So don't think that just because you only got to finish 1, that's a bad sign. Honestly, when I interview, I tend to ask very complex, kind of multifaceted questions. So I usually only get to 1 question, no matter how good you are. So this is typical. Most interviewers ask 2, but not everybody. So yeah, you can kind of expect 2, but don't think that just 1 means anything one way or the other. Okay, So with that, I'm going to talk about different types of questions and how to do well in them. First thing I'm going to talk about is behavioral questions. So these are all the kind of questions about your prior background. I'm going to talk a bit about how to prepare for those. One thing that's useful for most people to do is prepare a quick walkthrough of your resume. So the structure I've found works well for almost everybody is the very first thing you say is kind of your headline. I'm a software, your interviewer asks you something like, tell me about your background, walk me through your resume. Very first thing you say is, I'm a software engineer, wherever your title is, at such and such company. Then drop back to the beginning of your career. Usually college, sometimes you might start off talking about a particular job, and then walk through chronologically from there. You don't need to go overboard. You don't need to spend a ton of time in any one area. Just give the brief little highlights. This is not the time to go into detail in particular situations or accomplishments or things like that. However, there's a few things you can do to make your kind of pitch stronger. The first thing is telling the interviewer things that kind of demonstrate that you are successful. So that can be features you've built. It can be saying something like, I scaled the system from 1 million to 10 million users, something like that. But it's not always an accomplishment. So if I were interviewing somebody and I heard something like, and then I left company 1 when my old manager recruited me out to join his startup. That's not an accomplishment, being recruited out by your old manager, but it does show that you're successful. So think about those things that will make the interviewer say, they seem to have done a pretty good job there. Second thing to look for is, second thing to think about is, what do you want your interviewer to ask you about? What are your interesting technical challenges or other stories? You can kind of guide your interviewer there. So if you say that spent the last 3 years at company A and been focusing on a lot of different things, I've scaled the system from 1 million to 20 million users. I've also done a major re-architecture of the data store. It's natural for your interviewer to follow up with, oh, so tell me about that re-architecture. Tell me about that scaling. So think about, what do you want to talk about, and guide your interviewer there. It's a win for you, and it's a win for the interviewer. They want to understand your best accomplishments. The last thing here is hobbies. Realistically, I've done a lot of interview coaching, and when you get down to it, most people don't have hobbies that they're that compelling. And that's fine. It's not don't think it's a bad thing if you don't have any hobbies. Like if you're busy with, family, friends, and work, fine. But if you do have hobbies, think about mixing them in. It almost never hurts to say a hobby. So you can always, when in doubt, just say what the hobby is. But think about, when you talk about your hobbies, what's the best way to talk about them? How can you frame them in the most positive, relevant light? For example, if you like to run. So one person I was coaching, interview coaching, liked to run. They're really into working out. Okay, you can say it. Won't hurt you. Why not? But as I got into more discussion with him, it turned out that he had signed up for a 100-mile ultramarathon. That's running 100 miles, which is insane. But he actually quit it. Part of why he didn't actually tell me initially was he kind of saw it as a failure. He had signed up for this 100-mile ultramarathon, quit at mile 60 though, so he never finished it. And the reason he quit was that he got injured at mile 30. So he viewed this as kind of a failure. But what I heard was, wow, that's incredible. First of all, you signed up for an incredibly hard challenge. I mean, running a marathon is hard enough. He's running 4 marathons back to back. That's an incredibly hard challenge. So he's willing to take on, obviously, very hard challenges. He did a huge amount of it. I mean, 60 miles, yes, you didn't complete the whole 100 miles, but 60 miles is a lot. So you actually pursued a really hard challenge. You not only signed up for it, but you did a lot of training to get there to be able to do 60 miles. And he did those 60 miles, half of which were when he was injured. So this is not, it's obviously not a technical accomplishment, but it is showing some very relevant things. Risk-taking is relevant. Persistence is relevant. Willingness to take on an incredibly hard challenge, that's absolutely relevant. So think about your hobbies with that perspective. Take the hobby and figure out, is there something that is particularly relevant from it? And try to reveal that information. And certainly any technical hobby should be mentioned. Learning a new programming language, I've been getting really interested outside of work in functional programming. Definitely relevant. Doing hackathons, coding competitions, building an iOS app, even if you've never launched it, even if it's a failure. Any technical accomplishment, any technical hobby, definitely mention that stuff. Then, go through your past work, think about it, and pick out a couple projects, at least one, maybe 2, 3 projects that you're going to be particularly well prepared to talk about in detail. Find things where you were really central to some of the hard or cool parts. And then go through your past work and all of your past work and be prepared, especially those 2 projects, but really all of it. Be prepared to think about some of the normal follow-up technical questions people ask. So what were the challenges? What were the technical decisions made? What were the implications of those? Why did you pick these technologies? What were the hardest bugs, etc.? Be prepared to answer a lot of those technical questions, but also think about the softer side of it. So what was the teamwork situation like? Were you leading or you kind of a follower? How did you lead? If you led something, what did you lead? How did you show leadership? What were the kind of interpersonal conflicts, challenges, things like that? So think about not only the technical side of the project, but also the softer side of that. And then be very well prepared to really talk about what you personally did, and also think about what would you do differently. So at that point, it's kind of important, and I'll wrap up here talking about behavioral questions, but it's really important to think about that Facebook wants to identify people who will perform well here. So yes, that's about people who are technically knowledgeable and passionate and all these kind of things. It's also about people who work effectively on teams and who people would enjoy working with and who would be able to contribute good work. So the people I interview when some people I interview, they tell me that basically they thought the project went great, they wouldn't do anything differently. Some people will get very defensive when you ask them, what would you do differently? They're kind of defending every technical decision they made as perfect. That personally starts to worry me a little bit because there's no way a project was done perfectly. So if you're telling me it was perfect, you're either unwilling to admit to mistakes or you're unaware of what those mistakes are. Either one is a problem. I want to find people who, generally speaking, do great work, but they're also aware of the issues there. So think about your projects from that perspective. Be open about the issues and the mistakes and the weaknesses. It's far more impressive to me to hear somebody be open about the mistakes they made than to act like it's all perfect. So that's what I'll say about behavioral questions. I'm now going to move on to the technical side. So one other type of question that you should expect is design questions. So I'm going to talk about design questions from the perspective of system design and scalability, but understand that whatever your focus is, you'll probably get design questions that focus a little bit more around that. So if you're a front-end developer, you're going to get questions that are more about front-end architecture, maybe APIs, things like that. So this is from the perspective of system design, but parallels with these other design questions. What I also want to add in here is that you should expect design questions relevant to your background. That doesn't mean identical to your background. So if you've been spending a long time building, say, working on search products, it doesn't mean you'll get a design question that is, design a search engine. So relevant, but not identical to your background. All right, so I'm going to talk about design questions now. These questions intimidate a lot of people, largely because they think there's some magic to them, they think they have to know a lot more than they do. The way you should approach design questions is with this acronym, would you? And what this means is just, what would you do at work? That's how you should approach them. If I were your manager and I said, hey, I need you to go build a system like TinyURL or Bitly, hopefully you wouldn't say, okay, great, and then run back to your office, spend 3 weeks building it, and then come back and say, ta-da, I'm done. That would probably be a disaster, right? It wouldn't be the right technologies. It, be like, oh, actually, I need this to be an internal API. You never even built an API. So hopefully, in the real world, you would take an approach that's more like this. You'd say, okay, tell me a little bit more. What do we need? What are we building this for? You'd scope the problem a bunch. Then maybe you'd get an initial design of the system. And then you'd think, okay, does this really work? And you start going into more detail, really thinking through the different problems, and then go about trying to solve the problem. It'd be a very iterative process. This first piece, scoping, is super important and something that far too many people just gloss over. The scoping piece means stuff like if you're building TinyURL or Bitly or service like that, scoping piece means asking questions like, is this a website or an API? Is this, are we going to allow people to have, enter in their own little short URLs, or are we going to, just auto-generate all the URLs? So scoping means stuff like that. Another question I often ask, though, is how would you build something like Amazon's product rank system? So every product on Amazon has a bestsellers rank associated with it. So if you look at, say, a book, you might see, oh, it's the 1053rd best-selling book. How would you build that little component? So scoping here means you would want to ask questions like, is the rest of the system fully built? Presumably, yes. But it also means something, you might also want to ask a question like, well, what do we mean by bestsellers rank? When I've asked this question, a lot of people just gloss over this. They assume they know what best-selling means, and they don't define it. And that's a problem. What if, in the real world, a customer or your product manager or whoever said, hey, I need you to go build this best-selling thing, and you didn't spend the time to figure out what they mean by that? You could spend forever building this other thing, and that's not really what we need. So what I tell somebody who asks this is, no, best-selling actually means over some window of time. And that's a very different design, right? Having a number that increments at every single sale for all of history is very different than a sum of some sliding window. You might want to know things like certainly over what window of time is that best-selling rank. Something like, does the data have to be completely accurate? Or is it, plus or minus 10% in the ranks is enough? Does it have to be updated every single sale? Probably not. So you want to ask these questions. Take that scoping part very, very seriously. Then, when you go on to the other components, just start to say, okay, well, here's a naive idea of the system. A very simplistic system might be we have a front-end layer, an API layer, and then a data store, maybe an analytics engine over here. And that's kind of like a brute force naive system. Go up to the whiteboard, use the whiteboard to do this, and then you start going into more and more and more detail. Think when you're doing this, what are the complexities? What are the simplifications? Where are the different challenges or trade-offs or bottlenecks you might be hitting? So in the case of TinyURL or Bitly, if every single URL hits the data store to grab the associated URL, that might create a little bit of a bottleneck. So maybe you want to put in a caching layer in there. So start going into it in more and more and more detail. Think about the trade-offs, the challenges, the bottlenecks, and then go and fix those. Discuss this top-down. It's not, take one component and then just dive into it in a ton of detail. I've seen people I interview who they get this initial sketch for this Amazon product rank, and then they take one thing like the database, and they start going into a ton of detail on all the different database tables and this and that, and they don't go into the rest of the stuff. They kind of lose perspective. And a lot of what they design may not even be the right thing because they didn't think about it. They didn't think about how these tables are actually tied into the rest of the system. So take it top down, a little bit at a time. Don't just take one component and dive into it in a ton of detail. The behavioral aspect here is super important. You want to strike this balance between driving the process and being a great teammate. And it's actually less a balancing act and more that they really go hand in hand. driving means that you should fundamentally stay in charge. You should kind of act like you're the senior engineer. You're driving the discussion. You're figuring out where to go into more detail. You always have more things you can talk about. You're open about the trade-offs. So you're driving the process. Some people I interview, I ask a question and then they give me a 30-second response. And I feel like I have to just pull them through the problem and direct them at every single step along the way. That's not great. I want someone who can really take technical leadership. There's other people I interview who are kind of dismissive of me, and they make me worry about what would it be like to work with them on a team. So I ask a question and they kind of brush it off, they dismiss it a little bit. They probably aren't trying to do it, but they are being dismissive of the issues I raise. I'm not saying here that every time I say, won't this be an issue? You should say, yes, absolutely, and then just immediately concede. Maybe it's not an issue with your design. Maybe I'm wrong that I thought it was an issue, or maybe I knew it was an issue, but I want to see if you're thinking through why it's not. Either way, the point is not to concede to the things the interviewer says, but to really give it some careful thought and some analysis. Just like you would hope in the real world somebody would do. I would hope in the real world, if I were working on design with somebody, that they could hopefully lead the discussion, but even if I weren't leading it, even if I, maybe I know a little less than them, that they'll still take what I say seriously. So strike that balance. And again, use the whiteboard. Some people sit in their chairs a whole bunch. Use the whiteboard, it's there for a reason. And this, by the way, this discussion of driving versus being a good teammate, I'm talking about this for system design, but this is absolutely the case in algorithm questions as well. You want to drive the discussion of algorithms, but you also want to be very sensitive to the things the interviewer says. Last thing here I'll talk about with design is preparation. So preparation, again, this is from system design, but whatever your focus area is in technology, it parallels with that too. One thing that's very useful to do is go read about the design of different systems. So go read about Google's infrastructure and Twitter's and Quora's and yes, Facebook's. The idea here is not to go and study and memorize the infrastructure of any of these companies, including Facebook. You don't really need to know all about Facebook's infrastructure. The idea here is just read these different things and start to identify the patterns. Really, just memorizing this different infrastructure, these different pieces of infrastructure won't help you that much. What you want to do is really learn and think about them. Think about what are the fundamental differences in Google's problems versus Twitter's. Why have they chosen different architectures? Even for something for say a data store, how are they the same? How are they different? One answer to that is, okay, Twitter has to be real time in a very different way than Google search. How does that influence what they're doing? So the idea here is think about what they're doing, not just memorizing what they're doing. So be very, very analytical here. And then you'll see a lot of patterns come up as you do this. You'll start to see different ways of scaling large databases, different ways of handling task queues. Go use those as jumping off points. Also, go learn about the different piece of infrastructure or technologies relevant to your focus area. So for almost everybody, that might be learning the basics of the web stack. Some people might also want to learn about REST or things like that. But go learn the major pieces of infrastructure technology, et cetera, that are relevant to you or even more broadly relevant. And then the other thing that can be useful to do, particularly if this is something that comes as a little bit challenging or intimidating to you, is practice a little bit of back of the envelope calculations. It's very common that I interviewed somebody a little while ago and I asked them to build an RSS reader. In order to do this, they need to figure out how much of the database can fit on one machine. Can it all fit on one machine? And that required thinking about how many users, about how many URLs, how many feeds would each person have, about how many of those feeds would be active, how many posts per day or per window of time, how big is each post, how many megabytes, how many whatever. And so they have to do these back of the envelope calculations to figure out what's realistic to fit on one machine. Practice that if it's not something that comes naturally to you. one piece I want to leave you with here before moving on to algorithm questions is, and I really want to drill this in, these are fundamentally problem-solving questions. So yes, learning these different infrastructure pieces, technologies, etc., can be very useful, but fundamentally they're problem-solving questions. You're not asked to design a system like tinyURL or Bitly to see if you already know how to do that. You're being asked because they want to see how would you do that. So fundamentally, they are problem-solving questions, not tests of knowledge. So just keep that in mind both as you are preparing and as you're going into the actual interviews. They're problem-solving, not knowledge questions. With that, I'm going to switch to talking about algorithms. So algorithm questions are, you'll almost certainly get some algorithm questions. The reason why they're asked is a good chunk of it is analytical skills, problem-solving skills, assessing that. Another piece is seeing your communication skills. What is it like to work with you? What is it like to solve a hard problem with you? Can you make good trade-offs? Do you think about things as trade-offs, or just this is the way to do it? And then one thing that I really like to see is I like people who are at least willing, but ideally eager to solve hard problems. So by contrast, I interview some people who are kind of what I refer to as mentally lazy. They're not necessarily dumb. I'm not saying they're necessarily dumb, but they can be actually very bright and still be what I call mentally lazy. These are people who just don't want to think. It's correct, and as long as it's correct, it's fine. They don't care if the code is, has terrible style. They don't care if it has terrible variable names. They don't care if it's poorly organized. They don't care if the algorithm is really slow. Correct is good enough for them. And that worries me a little bit. I want to work with people, I want to hire people who are excited about solving a hard problem. And so that's one thing I like to look for. Are you at least willing, at the very least, but ideally excited about solving a hard problem? And another component of this is just finding people who have a strong foundation in computer science. What does that mean? I don't mean you must have a CS degree, because there are plenty of people who get hired who don't have CS degrees. But you can have a strong foundation in computer science without that. Here's what I'd say is the must-have knowledge. This is the must-have knowledge. You can do more than this, absolutely, and don't let me stop you. You can go learn Dijkstra's algorithm and topological sort and a lot of these more complex algorithms. They won't come up a whole lot, but there's no hardened, cut rule for this stuff is fair game for an interview and this stuff is not. So you could go learn that. It could come up. I don't see it come up a whole lot. These are the topics that I think are really, really fundamental that you really need to have, where if I were interviewing a candidate and they didn't have some of this knowledge, it could present a problem. So you'll see a lot of stuff about array lists, hash tables, really, really important. Sorting and searching algorithms, you certainly need to know those. One thing that is super important is big O, time and space. This is the topic that I'd say when I do interviews with engineers at startups, I'd say about half of those people claim to be comfortable with big O. The other half admit that they're very much not comfortable with it. But about half claim to be comfortable with big O. Of those, 80+% are not quite comfortable enough. They're still making a lot of the common mistakes. So, play the odds here. You're probably in that bucket of people who isn't quite comfortable enough with big O. So spend a bit of extra time making sure you're really, really comfortable on the basics. And then last topic I'll mention here is recursion and memoization and dynamic programming. Practice recursion. It comes up a lot in interview questions, and you may not have a lot of real-world experience with it. When I say dynamic programming, though, I'm not talking about these super famous dynamic programming problems that you hear about in big, thick algorithms textbooks. Again, you can learn that. I'm not stopping you, but what I'm talking about more is the pattern of practicing memoization and dynamic programming problems. It's a pattern that comes up in a lot of interview questions, and it's substantially easier once you get used to seeing that pattern. So practice some of those problems. For preparation, as I said, really master Big O, that's one of the first things I would do is just make sure you have a very strong foundation in what that is. Then go and implement that whole list of data structures and algorithms. Go implement all of those from scratch. It's unlikely at Facebook that you'd get asked something like, implement a binary search tree. You could, it's just actually kind of an easy, boring problem. So I don't know, I wouldn't ask it. But you could get it. It could happen. But more likely what would happen is you'd be asked some modification of it. So one question I ask does not require you to implement a binary search tree by any means, but if you aren't very comfortable with the implementation, you're going to have a lot more problems on it. So practice implementations. It'll really help solidify your knowledge. Then practice on real interview questions. And there's a ton of resources for this. Career Cup is one, Glassdoor is another. What I'd mostly stay away from is people who write blogs that are like, top 10 crazy questions. Like, those are picked because they're obviously like crazy questions, so they're not really representative. But practice on real interview questions. You can go read algorithms textbooks and things like that. It will help you, but the knowledge is generally beyond the scope of a normal interview, so it's not quite as applicable. It's best, in my experience, particularly if you're short on time, to actually practice on real interview questions. Really important here, though, code on paper. A lot of people don't spend enough time practicing this. You forget how much a computer kind of holds your hand. You have syntax highlighting, and so you kind of know when you write the wrong thing. You might have some code completion. You might, when you open up a new file, get a whole bunch of templated code that pops out in front of you. Ask a C developer or a C++ developer something as simple as write hello world, and a ton of people are unable to do it because they don't usually have to write code completely from scratch. So practice coding on paper. There's actually a more complex and impactful reason why it's so important to practice code on paper. When you've been, it's not just that you have syntax highlighting, code completion, and all these other nice features on a computer. It's also simply that computers are faster. You can type a lot faster than you can handwrite. So what you've done, and you haven't totally realized you've done this probably, is you've gotten used to a pattern of, oh, well, if I understand code, the algorithm I'm about to write about this well, I'm going to start just coding. If I make a mistake, I'll fix it, whatever. I'll realize it, I'll test it, I'll restructure my code, whatever. It's only 10 or 20 lines, so I'll just go ahead and do it. So you look for a level 6 understanding on pen and paper, or on a computer. When you're writing on pen and paper, it's just slower. And that means that if you start writing the wrong thing, it takes a lot longer to get back on track. You spend a lot more time writing the wrong thing. You can't just throw in a new test case and rerun it. Every mistake you make, every bit of confusion is far more powerful and far more damaging than it would be if you were on a computer. So you want to get very comfortable. With coding on pen and paper, because you want to learn to slow yourself down. Take a moment before you start coding to really make sure you know what you're about to write. And the best way to do that is just get comfortable handwriting and get comfortable with, hey, I really need to understand what I'm about to write before I write it. You can't cut corners here. You also just want to know about how long it's going to take you to code something. So practice coding on pen and paper. Then do mock interviews. You can, there are various mock interview services out there to practice interviewing. Those are great. You can do those. You can also just grab a buddy and practice interviewing each other. In fact, it's really useful. One thing I've done when I'm coaching people is, particularly coaching a larger team, is I'll often have people interview each other. Because it's actually really useful for somebody, particularly those who are more nervous, to try being on the other side, try being an interviewer, because you'll start to just naturally do a lot of the things that interviewers tend to do. So it's actually useful to practice being an interviewer as well and see what it's like from their side. So do mock interviews. Then the last thing here, push yourself. Too many people look at interview preparation as a quantity game. They're going to try to learn as many problems as they can before writing code or before going to the interview, and it's not really what it's about. It's more about quality. Spend time really pushing yourself. When I ask a question, my assumption is that you don't know how to solve it, and that you're going to, that means you're going to be struggling. You're going to need to be comfortable with seeing a problem, it being hard, and finding techniques to make progress. If your technique to solve a problem when you're practicing is to look at the back of the book, well, you're going to be kind of out of luck in an interview. So really get comfortable pushing yourself. If you're using Cracking the Coding interview, in the 6th edition, there's a whole bunch of hints there. Use those. They're there for a reason, but try not to use them, or try to use them as little as possible. So if you have to use a hint, look at the hint, read it, and then try to make as much progress as you can before going on to the next hint. Do as much as you can to push yourself through the problem before you look for more help, because that's what you'll want to do in an interview. So push yourself as much as possible. So with that, as you saw on one of the last slides, one of the things I stress a lot is really, really understand Big O. So I'm going to give a very, very quick crash course on Big O. This is not going to teach you everything about Big O in 5 minutes or whatever. It's going to be a very quick crash course. For people who know nothing about Big O, this will hopefully just kind of give you a taste of what it is. For people who have a bit more understanding, you'll hopefully kind of jog your memory about some of the common mistakes, and hopefully you'll avoid those in the interview, but at least there'll be a little jumping off point for you for, hey, I need to understand this a bit better. So we'll start with some more simple things. Okay, first problem here. We'll start with the basics. We have a for loop. It iterates from, and this is all in pseudocode, so don't worry about any particular language you need to know for this. We have a for loop that iterates from 0 through n. What's the runtime? Well, Big O is essentially like, this is a bit of a simplification, but an equation to discuss how things scale with time, how the runtime will scale with time. So in this algorithm, this little bit of code, the runtime will scale linearly with the size of n. So we would say it's O of n. Basic stuff. All right, we're going to get a little more interesting now. Here we have nested for loops. The first one goes from I equals 0 to n. Second one goes from j equals 0 to n, and it prints the pair ij. So this just goes through all the numbers between 0 and n and prints all the pairs. One thing we can do to save the runtime is we can say, well, if we're printing all the pairs of values in, between 0 and n, there's n squared pairs, so the runtime should be O of n, which it indeed is. The other way we can look at it is the inner for loop takes O of n time, and that's run n times. So the runtime will be n times n, or n squared. Both perfectly valid ways of getting to the answer. OK, more complex, slightly more complex. So I'm getting a little more interesting here. Now we have a for loop that runs from 0 to n. And within the for loop, it checks to see if n is even, and if so, it prints it. So it prints all the even numbers. Now, as you may know, this is still O of n, because we're still the for loop that goes from 0 to n. Just because it only prints stuff half the time, that doesn't change the runtime, because we're still going through all of those values between 0 and n. So it's still O of n. Even if we did, though, even if we were able to jump from 0 to 2 to 4 to 8, or from 4 to 6 to 8, that would still be O of n. In Big O, we drop constants. We don't say something is O of 2n. We say it's O of n. Because what we're concerned about saying is, does this scale linearly? And both n and 2n scale linearly, so we don't we don't include constants. And this is one of those first things that a lot of people make mistakes on. When I hear someone describe a runtime as 2n or 2k or something like that, it's kind of a sign to me of, OK, this person doesn't quite get Big O. So keep that in mind. You drop constants. OK, next example. Here, we're printing the evens first and then the odds. So 2 for loops, both from 0 to n. One checks for if it's even, prints it. One checks if it's odd, and then prints it. The first for loop is O of n. Second for loop is also O of n. So the total runtime is O of n, not O of 2n, as I said earlier. You don't include constants. 2 O of n for loops, that's O of n. All right. We're going to start getting a little bit more interesting. Before we had printed pairs, we were printing all the pairs from 0 to n. Now we're printing all the ordered pairs. So we have I from 0 to n, and then j starts from I and goes through n. So it doesn't start at 0, it starts at I instead. And we're printing the pairs. We call this ordered pairs because we don't print all ij's. We only print the j's that are bigger than I. So it's ordered pairs. One thing we can look at here is we can say, well, this I, when I is 0, j goes from 0 through n. When I is 1, j goes from 1 to n, then 2 to n, then 3 to n, then 4 to n, then 5 to n, etc. So whereas printing all the pairs was like we're printing a grid that's n by n, here we're still kind of printing a grid, but we're only printing the top right side of the grid. So we're printing half the grid, so that's n squared over 2 things we're printing roughly, which again is O of n squared. We don't say O of n squared over 2 because we drop constants. So O of n squared. All right. So go back then. So now, again, printing ordered pairs, but now we have 2 different arrays. Here we're printing from I equals 0 to a dot length. So going through all elements in A. Within this, we're printing going from j equals 0 to b. And we're printing the pair ij, or a of I, b of j. A lot of people here, and this is one of the most, probably the most common mistake I see people make. A lot of people here will say n squared. They see nested for loops, and they think, aha, nested for loops, n squared. Be very, very careful here. When you say O of n for some algorithm, you mean O of n where n is some particular thing. It's not, inherently O of n. Inserting a node into a balanced binary search tree or finding a node in a balanced binary search tree is not inherently log n. It's log n where n is the depth of the tree. It's also O of n where n is the total number of nodes in the tree. You can't just say O of n or log n. It's not inherently those things. So when people describe this, as many do, as n squared, that's not quite correct, because what would n mean? N can't be the length of the array because there's nothing in here saying A and B are the same length. So you have to say it's something like O of A times B, O of M times N, something like that. That's a very, very, very common mistake. It can cause huge problems when people don't get that. So different inputs, every variable in runtime has to have a meaning. Different inputs has a different variable. So O of A times B, unless, of course, you were told that A and B were the same length, in which case saying n squared would be perfectly fine. So be very careful there. Different variables means a different runtime. All right, now we're getting a lot more complex. Here's a big chunk of code. Don't just try to look at this and say, aha, it's this thing. Just walk through it step by step. So this is code that first walks an array of people and does some simple max function. Then it walks through all the people all over again. And it looks like we have a nested for loop. So this is going through each person. Nested for loop here that goes walks from every year from their birth year to their death year and increments something. And then we go through another array. So let's just take this piece by piece. OK, first step is we're walking through all the people. So I always like to use logical variable names in runtime. I don't like to use n, actually, because unless there's no ambiguity about what n could be. So I like to use logical variable names. So this step is O of p, because we're walking through all the people, where p is the number of people. I'm going to assume here that max is a constant time function, which it almost certainly is. So O of p. Then, for each person, and there are p people, we're walking through every year from their birth to their death. So this for loop here inside will be O of L, where L is the max lifespan. And then we're doing that for p people. So O of p times L. Then, third step here is we're walking through every year from the first person's birth year to the last person. And then we're going and incrementing something. So I'll let this be O of y, where y is the span from the very first birth year to the very last death year. And so that step is O of y. Note that y and L are not the same thing. This is walking through each person's lifespan. This is walking through the lifespan of the entire population. So it's not the same thing. If every person lives for a max of, each person lives for a max of 100 years, but we're, looking at all of the people who've ever lived on Earth, those are going to be very different numbers. So to get the runtime then, we add these things up. So that's going to be O of p plus p times L plus y. So that gets down to p times L plus y. One of the mistakes that people make with runtime is they get tripped up on when they add and when they multiply things. Adding is, I do this thing, I'm all done, it's wrapped up, I'm good, and then I do this other thing. That's adding. When it's, I do this thing for every time I do this other thing, that's going to be multiplying. So keep an eye out for that. I think most people understand this fundamentally, but they make a lot of mistakes there. OK, now we're going to get harder. So Fibonacci. This is a basic recursive code to get the nth Fibonacci number. So if we call fib of n. If n is 0 or 1, return 1. Otherwise, call fib of n minus 1 plus fib of n minus 2. Recursive runtimes are one of the things that I'd say the vast majority of people really struggle with getting. Because they want to look at it and they want to just say, it's easier when you see for loops or whatever to get the runtime. It's harder when it's like, well, this thing calls itself a bunch. What do you do? The way that I found works well for people to get the runtime is to actually walk through it, see what happens. Draw what I call a call tree. So fib of 6, I'm just going to run through an example. Fib of 6 calls fib of 5 and fib of 4. Fib of 5 calls fib of 4, fib of 3. Fib of 4 calls fib of 3, fib of 2, et cetera, et cetera. So it's happening kind of like a tree. So if we look at this tree has a height of 6. In this case, height of 6. In general, if you call fib of k, it'll have a height of k. Every level doubles the number of nodes, because each call calls out 2 more times. So if we have 1 node at the top, and then we're doubling, and we're going to have 2 nodes, then we double the number of nodes in the next level, and then double and double and double. If we do that k times, if we take a number and then we double it k times, and we start with 1, that's going to be 2 to the k. So that gives us a runtime of O to the k. Now this is you can go online and read more about this. It's actually a little bit of a simplification. For more complex math reasons that are way beyond the scope of this or a normal interview, it's actually slightly less than 2 to the k. But 2 to the k is a perfectly satisfactory answer. So O to the k. This is a technique that I found is very valuable for a lot of recursive runtimes to draw out this call tree. Now, as you might know, this is not the best way to do Fibonacci. One little optimization is to notice back here that we're calling Fibonacci on the same nodes more than once. So fib of 4 is called twice. Well, that's so stupid, right? Like, why call fib of 4 here if we already did it here? We should only compute it once. It's not like the answer changes. Likewise, why call fib of 3 when fib of 4 also called fib of 3 down here? We only need to do these things once. So this is getting into a memoization approach. So we'll add in what's essentially operating like a hash table that says, OK, if we haven't called it before, haven't computed fib of n, compute that, and then return the computed value. Now when we draw out the call tree, it looks a little bit different. Fib of 6 calls fib of 5 and fib of 4, but it doesn't go anywhere after fib of 4 because fib of 4 is already computed. Fib of 5 calls fib of 4 and fib of 3, but fib of 3 would have already been computed, so that one doesn't get called here. If we draw out this thing, we don't get a tree anymore with, not like a full, complete tree that's huge like the last time. We actually just get something that looks much more like a straight line down here. That straight line goes to a length of n. So that gives us a runtime of O of n or O of k. So this is actually a broader point I wanted to make. When you see really, really slow recursive algorithms, think about memoization. Look for those repeated problems. OK, so that's the very, very quick crash course in Big O. This is not meant, as I said, to teach you everything you need to know about Big O. This is just kind of the basics, some of the common patterns that you'll see come up. Please, please go practice Big O. You need to know it really, really well. It's not about knowing the Big O time of all those algorithms and data structures I put up earlier Yeah, absolutely, you should know that stuff, but the point is more that you need to be comfortable enough with Big O that if you see a new, if you're designing a new algorithm, which is what you'll really be doing in interviews, you'll be designing new algorithms, you'll be able to immediately state the runtime for that algorithm. And then you'll make this or that change, and you'll say, okay, now it's this, now it's that. So you need to be really, really fluid with Big O. So go practice that. With that, I'm going to switch to talking about how to actually solve algorithm problems. Okay, so I wanted to go and set a bit of expectations here. Because a lot of people walk in thinking that they need to know a lot more than they do. So I like to set expectations. First of all, you don't need to know the answers to the problems I ask. In fact, if you do already know the answer, please just tell me, oh, I've heard this before, and I know how to solve it already, and here's how you do it. Or I've heard something like it, whatever the case is. You're not expected to know the answers. You're not expected to solve the problems immediately either, or even to code perfectly. That's not to say that shouldn't be your goal, and I want to make that very clear. The faster you can solve the problem, great. The more perfect your code is, great. People often ask, is it okay to have a bug in your code? And it's a very tough question to answer because it depends on what you mean by okay. I'm trying to evaluate your problem-solving skills. And it's not a binary thing. It's not you are good, you are bad. Or I'm trying to evaluate your coding skills. Again, it's not binary. It's not you are good, you are bad. The fewer bugs you have, the more quickly you solve it, the more likely I am to think you're a great coder, you have very strong problem-solving skills. The point I'm making here is not don't worry about whether how quickly you solve it. Don't worry about bugs. Not at all. It's more that the more it's not like not knowing how to solve it immediately is going to result in a rejection, or having a bug in your code is going to result in a rejection in and of itself. I rarely ever interview somebody who, when I ask a hard problem to, just says, aha, this is exactly how to solve it. I've never heard this before, but I've just solved it right now, and here, let me write up perfect bug-free code. It just doesn't really happen. So shoot for that. Try to solve it as quickly as you can. That helps demonstrate good problem-solving skills. Try to code perfectly and all that, but I just want to set expectations and don't want people to think that they failed. And it's not a binary thing anyway, but that they failed because they had a bug or struggled a little bit. Everybody's kind of struggling, and most people have bugs. What I do want to look for is I want people, as I said, who are excited about solving a hard problem. I want people who will drive through the problem. As I said, there's some people who are kind of mentally lazy who see a problem and they have a solution, it works, so that's fine. Or maybe they don't even think about if it works. They just, the first thing, there's here's one way of doing it. And they don't even think through whether or not it works. I want you to drive through the problem. I want you to look for a great solution, not just any old thing. So I want you to be striving for something that's more than just correct. It's actually a great solution. I also want you to keep trying when you're stuck. For some interviewers particularly, it can actually be like a big red flag if somebody says I don't know how to, I don't know how to do it. I don't know where to go from here. For some interviewers, that's a big red flag, and I'm not quite as harsh about that, but I understand their perspective. What if in the real world somebody said, this is a hard problem, I don't know how to do it, therefore I can't? That could understandably be a problem in the real world too. So keep trying when you're stuck. Getting stuck is normal. It's normal to get stuck. It's normal to have hard problems. The thing is, you want to keep trying, even when you're stuck. And you want to keep trying even once you have a solution. Make sure it's a great one. Look for a great solution. Next thing is, pay attention to me. Pay attention to what I'm saying. I've interviewed a bunch of people who, this is actually pretty common, when they give me a solution and I ask, and they kind of give it to me, and then they try to start coding and I stop them. But I say, okay, well, hold on. Does it work? And they think for a second. They say, yeah. And I'm like, okay. I give them a couple more, maybe 15, 30 more seconds, whatever, depending on the problem, to continue to think about. And then I'm like, let's take a step back. Are you sure that your algorithm works? Again, they think, yeah. Again, this happens over and over again. Pay attention to the things that your interviewer is saying. interviewers aren't saying things to confuse you. They're saying things for reasons. If they keep asking you, are you sure it works? That's a sign, right? If they ask you, are you sure you need 2 arrays? Maybe they're trying to indicate, hey, let's try to reduce the space a bit. I think you can maybe only get by with 1 array. So think about the things that your interviewer is saying. I talked about this from the perspective of system design and scalability and design questions as well. Think about the points the interviewer is saying. Listen to them. You don't have to immediately concede. If I say, are you sure 1 array wouldn't be enough? Don't just say, oh, absolutely, yeah, no, you can do it with 1 array without understanding how to do it. But you just want to listen. Pay attention to the things the interviewer is saying. If your interviewer ever says the same thing more than once, that's probably a reason. Right? That if I say more than once, are you sure you need 2 arrays? I'm probably indicating you missed it. Whatever I was trying to point out the first time I said it, you probably missed, and so pay attention to this time. So pay attention to what your interviewer is saying. And then write real code. Sometimes interviewers are okay with pseudocode, but it's unusual. Your expectation should generally be to write as close to real compilable code as possible. That said, this is not a binary evaluation. Ultimately, I'm not judging your code on % correct or some sort of fixed number like that. I judge your code based on the attributes I can derive from it. What is it indicating to me? If you are using a built-in linked list class and you call the method add and it's actually called insert in that language, I don't care. Personally, the fact that you called it add and it's actually insert, all that tells me is, okay, you're not comfortable enough with you haven't used a built-in linked list class that much recently. Okay, no big deal. I don't expect that you have. I don't care at all about that personally. Now, if you're writing single equals for a comparison in a language that, like most languages that use a double equals, well, that worries me. If you're not declaring your variables, that worries me. If you are not writing types in, if you're operating in, say, Python and write I++ when Python doesn't support that syntax, these things start to add up and start to be a bit more worrisome. So try to write as close to real correct compilable code as possible. Don't think that, I'm not saying that one little issue is going to be equal rejection. That's not realistic. But it depends on the issue, obviously. But try to write as close to real compilable code as possible. And then before I go on to the algorithm specifics, I want to make this very clear. Show me how you think about the problem. I'm trying to evaluate your thought process. It's not, I don't get a metric that says you need to solve the problem in this number of minutes or else, and that will give you this score. People often ask, how long do I have to solve a problem? Is 20 minutes enough? Well, it depends on the problem, and it's not about the time alone. People can take more time and do better than somebody who took less time. It's much more complex than that, but because what I'm trying to do is evaluate your thought process. If you're not talking out loud and showing me your thought process, I can't really do that. I also, I can't say, wow, that was a brilliant insight you made if you didn't vocalize that insight. So try as much as you can to talk out loud. If this is something that you particularly struggle with, one, most people who say that they have a really hard time doing this are actually okay here. People don't struggle as much as they think they do. But one thing to think about is if you can't tell me everything you're thinking about, notice when you're being quiet and try to give me at least the headlines of your thought process. So tell me, when you notice yourself being quiet for a little bit, say, just give me the headline. Oh, what I'm thinking about is how to optimize this piece. What I'm thinking about right now is how to, get rid of the second array. I don't think we need it. So give me at least the headlines when you're quiet and focus on that. That's something concrete that most people can do. But as much as possible, try to share your thought process with me. Okay, with that, I'm going to talk about how to actually solve algorithm problems. This is a handout you can get at crackingthecodinginterview.com. Click on resources and you can download that. You can also, the same auto response I mentioned earlier, g@gale.com, the subject FB prep, one word. That'll also give you an that's just an auto response. You don't need any body in the subject or in the email at all. Just a subject, FB prep is fine. So that'll give you a link to this handout. I really, really, really encourage you to actually use this structure when you walk through a problem. It was prepared after doing a ton of interview coaching, a ton of questions, and seeing a lot of the mistakes people make. And now, when I watch people interview and when I do interviews myself, a lot of the mistakes people make could be avoided if they just followed this process. So walk through this structure, and also pay attention. I would actually have this out in front of you when you prepare, and actually look through. When you're stuck optimizing, go actually look through these different things, the different things I say there. They're there because they avoid a lot of the mistakes I see. So I'm going to walk through this kind of flow chart you'll see in the top right. Again, I really encourage you to focus here, pay attention, obviously, and to use this when you're actually practicing problems. OK, very first step here, step 1, listen. Now, this is the kind of expected interview advice. It's the kind of thing everybody says: listen carefully to the problem, make sure you've heard it correctly, blah, 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 blah. I agree with all that 100%. Do listen to the problem. Do make sure you've heard it correctly. Do ask any follow-up questions. I'm saying one step further than that. I'm saying listen carefully to what I said, how I constructed the problem. Listen for clues. There are often little clues in the problem. And the interviewer may not even be thinking about them as clues, but they are often clues. A clue is, well, taking a step back, interviewers tend not to give you information you don't need. So every bit of information in the problem, they try to simplify problems as much as possible. They try not to give you information that's irrelevant. There are exceptions, but they tend not to do that a whole lot. So generally speaking, any information given in a problem is there for a reason. So that means if you hear something and you think, I don't really need that, I can solve the problem without that, it probably means that you can solve it, but you can't solve it optimally. Every bit of information should be generally useful for something. I'll give a hypothetical problem. You have 2 arrays, sorted and distinct. How would you find the number of elements in common between the 2 arrays? So deconstruct the problem. You have to find the number of elements in common. OK, well, that's the question itself. That's why I gave that information. Obviously, you can't solve the question if I didn't state what the question was. You need to find, you're told that there are 2 arrays. Well, again, the problem wouldn't really make sense without knowing that there's 2 arrays. You need to know how many arrays there are in order to find the number of elements in common. OK, so it kind of makes sense why I told you that. But why did I tell you that the data is sorted? Even with 2 unsorted arrays, you could find the number of elements in common. So that likely means is that the fact that the data is sorted actually changes the optimal solution. Yes, you can find a solution, even if it's unsorted, but it probably changes the optimal solution. So pay attention to those clues. I'll give a different example of what a clue might look like. This is a little bit different scenario. So first of all, starting off with the definitions. An anagram, or the anagrams of a word, are all the permutations of a word that exist in a dictionary. So for example, the anagrams of rates are aster, stare, tasers, and tears. So the question is, how would you build an anagram? And as I state this, pay attention to the clues. See if you can figure out what the clue is. How would you build an anagram server or website? So given a word, you're given some list of valid English words, and you want to print all anagrams of that word. Or print or return. So if I said rates, then you'd return, your server or website would return aster, stare, teaser, tears. So how would you design that website or server? And I'm going to preface this with saying this is an algorithm problem. It's not system design. So let's look at the information I told you and what I've put in the problem. So I told you I told you what an anagram is. It's pretty clear why I did that. I can't really ask you to do something if I don't tell you what the term means. OK. I told you that you need to print or return all anagrams of that word. Well, that's the problem itself. I told you that you're given a list of all valid English words. Again, the concept of an anagram is permutations that exist in dictionaries. So clearly, you need a dictionary. So makes sense why I gave you that. But why put it on a server? why not just say, I mean, I told you it's an algorithm problem anyway. Why not just say, okay, write a function that, given a word and a list of valid English words, prints all anagrams of that word? Why did I say, go do this thing on a server, though? Likely what that indicates is, hey, the fact that it's on a server actually changes the optimal approach. So what does a server let us do? Well, it allows us to have additional resources like databases or things like that. It allows us to cache things. One other thing, though, is that a server lets us pre-compute. And if you look at that, if you look at the anagrams of rates, aster, stair, tiers, these all sort to AERST. So what that means is if you took your dictionary and your server, when your server boots up, you can do this pre-computation step of taking your dictionary, sorting the characters in every single word, and then grouping all the anagrams together. So when I say, give me the anagrams of rates, I can say, OK, great, I'll pull out the AERST grouping, and I'll pull out all those words that's sorted to that. That approach makes it super fast on a server. We can do this pre-computation. We have to run through all the words, but if we do that once, that's not a big deal. And then when we say, give me the anagrams, it's going to be really quick to do that. This pre-computation step makes the server approach really fast. If it was just a single function run once, the pre-computation step wouldn't make any sense. There'd be no reason to build this whole anagram lookup thing if I only wanted a single one. So this server piece is incredibly important. You cannot do this pre-computation optimization. It doesn't make sense to do on a single, without it being on a server or something like that. So pay attention to these clues. If you miss the clue, then you kind of can't solve the algorithm without that, at least not optimally. So pay attention to those clues. And if you ever think you might have missed something in the problem, feel free to go ask the interviewer what the problem is or state it back to them in your own words. This goes back to what I said in the very, very beginning about, hey, your interviewer is on your side. They're not trying to trip you up with something like this. If you think you forgot something or you didn't get all the details, just ask, just clarify. It's fine. OK, step 2. Really, 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 really important piece here, and something that it's such a shame how many people don't draw examples or don't make as much use of them because it's such a simple thing to fix. Just draw an example and make your examples large and avoid special cases. It's really, really common for people to mishear a problem. And I think what happens is that people get nervous. It's an interview. It's intimidating. And maybe it's that when an interviewer states the problem, they get kind of caught up in, oh my God, are they going to ask me a really hard problem? And they miss some detail. They can interpret the problem in a very, very strange way, even when the problem was actually perfectly clear. So draw an example. An example is one of the first times when I'm like, no, you actually misheard the problem. So I say that example I gave earlier with, and think when I do this about what kind of example you might draw for this. 2 arrays, sorted and distinct, find the number of elements in common. I'll see people draw examples that have one array, and then it's very clear that it doesn't make sense. So draw an example, get the input, get what the output would be for that. Helps to clarify that you actually heard the problem correctly. But to make good use of the example, make it large and try to avoid special cases as much as you can. So for that problem I just mentioned, 2 arrays, sorted and distinct, find the number of elements in common, most people draw examples that look kind of like this. 2 arrays, great, OK, yes, they're sorted, yes, they have distinct elements, but they only have 4 elements. So they're tiny, and the arrays are the same length. And I never said the arrays are the same length. And they only have 1 element in common. It's, yes, it's an example, but it's a bit misleading because the arrays are not necessarily the same length. And it's also very small, and so it doesn't help you walk through your algorithm very well. A better example is something like this. Much larger. So you have 6, 7, 8 elements. They're not the same length. They have multiple elements in common. That's the kind of thing you should look for. The idea here is an example that is complex enough that your brain has to do at least a little bit of thinking. So compare this to, say, something like reading. If I just point to a word like big, as soon as I point to it, you will have read it. You can't turn off your brain from not reading it, right? You've read it by merely a glance. Likewise, with that first example with 2 arrays of length 4, even if I didn't underline the element common, as soon as I point to it, you will basically notice, oh, they both have a 12 right there. You're not going to learn much by trying to walk through and do it by hand. Something like this, with 2 arrays, 6, 7 elements, your brain has to do a little bit of study, has to do a little bit of work to get the right output. That's the kind of example you should look for. So something that's a little bit more complex and meaty. This is one of the quickest fixes to avoid a lot of problems down the road. Make your examples large and avoid special cases. OK, third step is get a brute force naive algorithm. Very, 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 very important here. Don't code this. I'm not saying to immediately state an algorithm and go and code it. Just state the algorithm. Well, one brute force way of doing is like this. That'll have this runtime, but I think we can do something a little faster. So I'm not saying go immediately code it. Please don't do that. Unless your interviewer wants you to. You can always ask. Your interviewer is not trying to trick you or test which algorithm you want to code or something like that. You can always ask your interviewer here, but just practice just state when you have a brute force naive algorithm, just go state it and state the runtime and then go into optimizations. The most important message I want to get across here is it's OK for your first algorithm to be slow. It doesn't have to be a perfect algorithm at first. I'm not, it just wouldn't be reasonable to expect that with a really complex problem, you'll immediately know how to solve it. These are supposed to be hard, challenging questions. So the first thing you come up with, it's OK, state it, even if it's really slow. The reason why this is so important is, first, if you did mishear the problem, the brute force algorithm will often make it clear that you misheard it. And yeah, it's unfortunate you misheard it, but it's much better that we realize this 30 seconds into the interview than 15 minutes in. And often your brute force algorithm will be able to say, that doesn't really make much sense, and then we'll realize you misheard it. It's also really important because not everybody can develop a brute force. Sometimes, there's some problems where the brute force is actually really challenging. There's other problems where there's a brute force that's pretty obvious, and there's still some fraction of people who will struggle to get there. So you want to make it clear that, hey, you're at least at that level. Thirdly, and perhaps most importantly, it's important because it's a really good jumping off point. A lot of optimizations can be made by starting with the brute force. So start with the brute force. Again, I'm not saying to go and you come up with an algorithm and immediately go and code it. Just state it, state the runtime, and then you can ask if they want you to code or keep working on the algorithm. Usually you'll want to keep working on the algorithm a bit more. Then go and optimize it. So you have a brute force, go try to optimize this algorithm or come up with something better. I'm going to talk through a couple different ways of optimizing algorithms. Very first one I'm going to talk about is called BUD. Now, when I talk about these approaches, actually try to practice using them when you're preparing and in the interview themselves. So BUD is the first one. This means to look for bottlenecks, unnecessary work, and duplicated work. Bottlenecks. All right, so our first problem we mentioned earlier, 2 arrays sorted and distinct, find the number of elements in common between the 2 arrays. The brute force algorithm here, imagine I'm a candidate, I'd say, OK, well, draw this example and then say, OK, well, one way of doing it is just walk through the first array, and for each element in the first array, for each element in the first array, walk through the second array and look for it. And if it's in common, increment the intersection. And that'll be, of course, an O of A times B runtime, but I think we can do something a little faster. So that's like that, step 3 or whatever, the brute force. State the brute force, state the runtime, optimize it. And notice here that the runtime is O of A times B, not N squared. OK, so you have an O of B runtime, and that O of B thing that we're doing A times, that's a bottleneck. For every element in A, we're doing O of B work. So identify that bottleneck and get rid of it. So the bottleneck is this searching. For each element in A, we look through B. That's O of B time. Well, how do we make these kind of lookups or searches or sweeps faster? Well, we could throw everything in B into a hash table or a hash set. That'll be O of B time to do that, but then each lookup is only O of 1. So that'll give us an O of A plus B runtime and an O of B space complexity. We could do a binary search here on B. So that'll be an O of A log B runtime, and then O of 1 space complexity. And then, or we could walk through B and A and B with 2 pointers, kind of like doing a sorted, merging 2 sorted arrays. So walk through A and B with 2 pointers. And that'll be O of A plus B runtime and O of 1 space complexity. So the technique here is identify that bottleneck in the brute force or your algorithm, and focus on, figure out where is that bottleneck coming from, and then how can I get rid of that. Okay. Next thing to look for is unnecessary work. So new question. This is a question I've asked a bunch. It is not a math problem, despite how it might sound. There's nothing more than like very basic math you need to know. Just the question is, given the equation a cubed plus b cubed equals c cubed plus d cubed, find all solutions a, b, c, and d that are integers between 1 to 1,000. So we want to find all the solutions. Great. OK, just walk through. You want to find all the values of a, b, c, and d that work. Fine. Walk through all possible a, b, c, and d's and look for matches. So that's 4 nested for loops. This gives us a runtime of n to the 4th. And we're looking at this. Again, you wouldn't necessarily write out this brute force code, but I'm just doing it for demonstration purposes. So you have 4 nested for loops. And within this, we might notice, OK, well, we can make this a little bit faster by throwing a break statement here after the print. Doesn't change the big O time. It's important to note that. But might as well do it. It's easy. It's fast. It makes it a little bit better. So throw in a break statement here. But what that indicates here is that, well, wait, if we're saying we can put in the break statement, what we're saying is that there's only one value of D that works for any given A, B, and C. So yeah, not only can you break once you find that value of D that works, but if there's only one value of D, can we find it more quickly? And you can. I mean, imagine A were 17 and B were 53 and C were 32. If I just gave you that, if I just told you 17 cubed plus, whatever I said, 53 cubed plus 32 equals 32 cubed plus D cubed, I think I don't know when you learned this, 7th grade, you need to solve for D. So D is a cube root of A cubed plus B cubed minus C cubed. Just solve for D. So that's the necessary work. A lot of times the necessary work kind of comes up when it's like, oh, a break statement here or some minor little thing that may not even change the big O time, but it triggers a bigger thought about an optimization. And this one drops it down to n cubed. Better, though not still ideal. Let's jump back to the brute force. Another thing we can look for is duplicated work. So if we look at this brute force, we'll notice what we're really doing is saying, OK, for every A-B pair, generate all the CD pairs, and look for matches on their cube sum. So times when CD's what I'll call cube sum matches AB's cube sum. Then I change the AB pair and generate all the CD pairs all over again, look for matches. New AB pair, generate all the CD pairs, look for matches, etc. We're doing this CD work over and over and over and over again. It's the same list of pairs every single time. So maybe we should think, OK, well, can I just take that CD loop, pop it out, and just do it once? So this is the table. This is like all the CD pairs that we walk through. And then this here is our cube sum. And so what our algorithm is really doing, our brute force, is saying, OK, for each AB, essentially generate this whole list, and then look for times when AB's cube sum appears over here. And if we were to only do that once, we would probably want to just be able to look up on this column, right? So what if we took these CD pairs and actually just up front, rather than walking through this list this hypothetical list every single time, what if up front we just said, OK, let me just generate all the CD pairs and put them into a list that maps, a hash table that maps from a cube sum to the pairs that got us there. Then when I have an AB pair, I can compute that cube sum and pull it out of a hash table. And that's what this does. For each CD, put it into a hash table that maps from a cube sum to the pair that got us there. And then for each AB, just pull up the results, pull up the matches from the hash table. That drops us down to an n-squared algorithm. Even faster, though, or even different way, not actually faster, but a different way of doing it is we could even notice that these ABs also go through all the pairs between 1 and 1,000. So that means that these AB pairs are actually already in this hash table here. So rather than, once we generate all the CD pairs, we can actually just use the hash table directly and walk through all the groups in that hash table. So that's duplicated work. Notice when you're doing something over and over again and see, hey, is there a way of reusing this work a bit? So that's BUD. All right. Next approach is looking for space-time trade-offs. This is one of the most common things. A lot of problems involve hash tables. In fact, so many problems involve hash tables that I'm not even going to give a special hash table problem here because so many of my problems already involve that. But I'll give a slightly different version of this, which is more about pre-computation. So, new interview question. You have a matrix of positive and negative values, and you want to find the submatrix or the subrectangle that has the biggest sum where it has to begin in the top left corner. All right, so we want to find the rectangle with the biggest sum that begins in the top left corner. So, well, step 3, right, was generate any solution, no matter how slow. We want to find the rectangle with the biggest sum. Fine. Generate all of the rectangles, walk and compute the sum of every single one, and then just pick the biggest one. It's slow, but it'll work. Now let's walk through that and think a little bit more about what that does. What it means that we're doing is we're saying, OK, get the sum of the 6. That's the first rectangle. Next one is the 6 and 5, so add up the 6 and 5. Next one is the 6, 5, negative 9, so add up 6, 5, negative 9. Then 6, 5, negative 9, 2, et cetera, et cetera, et cetera. We go down here, 6, negative 2, 3. 6, 5, negative 5, 2, negative 2, 3, negative 2. So add up these 6 elements. Now we're adding up all of these 9 elements. We keep adding up the same things over and over again. We're like saying, add up these 9 elements, but we just added up 6 of those elements. So I mean, no reason to go through all of these, add up all those 9 elements, when 6 of them we already did, right? So let's at least reuse that work. This actually relates a lot to the duplicated work I talked about earlier. Let's reuse that work. We already added up these 6 elements. But now what about these other ones? Well, this negative 9, negative 2, well, we didn't add up all of those elements yet, but we added up these top 6 also. So we could try to use that rectangle as well, except that we'd be double counting the 6, 5, negative 5, negative 2. So what do we do? Well, that one we added up earlier too. So if we want to know the sum of these 9 orange elements, that's going to be the sum of this blue rectangle here that we added up earlier. We already have the sum to that. If we store all our prior answers, we already have the answer to that. Plus the sum of this green rectangle, which again, we already had the answer to. Minus, the only problem is that we're double counting this red square. Well, we already added up that square, so let's just take out that one, plus this last one. So that's going to allow us to pre-compute this. Then we can do that for the next one. The orange elements is the blue rectangle, which we just did now, plus the green one, which we did earlier, minus this overlap that we're double counting. So that's pre-computation. If you do that, in this case, you can get a much more optimal algorithm. You can do this in n squared time, if it's an n by n matrix. So because we can get the sum of each rectangle, given the prior ones, in constant time. So on a lot of problems, there's optimizations involving hash tables or pre-computation. So pay attention to those. Third approach, this is one of my favorite interview questions, and as it turns out, one of my favorite approaches. So, new question. You want to find all of the permutations of S within B. So you have 2 strings, S is a smaller string, B is a bigger string. Find all permutations of S within B. All right, so one thing here is I like to use logical variable names. So rather than using like A and B, M and N, something like that for variable names, I like to use logical variable names whenever possible. There's a little tip. Avoid some confusion. So S is a small string, B is a big string. Find all permutations of S within B. I've asked this problem probably dozens of times now, and pretty much everybody, 95% of people, pretty immediately have an algorithm That is, okay, well, brute force, find all permutations of S, look up each within B. It's slow, but it'll work, right? But, then they get really stuck. They get the runtime, usually with some help, and they realize it's S factorial times B. That's really, really slow. If you go back to the bottlenecks and necessary work, duplicated work, that S factorial is a bottleneck. You've got to get rid of that. I'll see a lot of people who will, start thinking that they realize it's really slow. This S factorial is like really, really, really bad. It's way worse than exponential time. Then they won't kind of prioritize things right. They'll see S factorial times B and they'll start thinking, oh, maybe I can take this string of length B and I can throw it into a trie, and I can do this and that, and maybe I'll be able to get down to B time. And in some ways, you can argue it's kind of silly because the S factorial thing is just going to kill your runtime. Got to get rid of S factorial, which means no generating all the permutations anymore. Got to get rid of that. So let's take a step way back to step 2, which is just get an example. All right, so we want an example of S and B. And so again, the idea here when you get an example is generate an example, have it be a big one, and try to avoid special cases. And then you should get an example, and then you just figure out what the output is. So this is an example S. This is an example B. As I talk about this, start looking for the permutations yourself. So this is S and B. I looked for here, intentionally made the example. I made B really big, and I also made S. S could have been a little bit larger, but I made it on the larger side. And I also tried to avoid special cases, so I made sure that S was not all unique characters. This is S and B. So that's our input. Now, okay, well, we need the complete example involves output. So what's the output? Well, you just want to go through and find all the permutations of S. Now, what's interesting here is I've done this dozens of times. Looks like my underlining is a little bit messed up, but I've done this dozens of times, and pretty much everybody can find all the permutations of S. Nobody really has problems with it. But what's even more interesting is that I've asked this dozens of times again. Pretty much everybody comes up with this algorithm that's find all permutations of S, look up each within B. Nobody has yet, after dozens of interviews with this, actually used their own algorithm to solve the problem themselves. Nobody does it this way. Nobody says, okay, all the permutations of S, so that's going to be ABBC and ABCB and ACBB and this and this, and all 12 of those permutations, and then goes and looks for every single one of those strings. Nobody does that because you don't want to hold all this stuff in your mind. You know that coming up with the permutations is just going to take a while. Pretty much everybody does a much more logical thing of just walking through this and looking at the first 4 characters. Is this a permutation? And then going to the next. Is this a permutation? Is this a permutation? Is this a permutation? And depending on your algorithm to do the is this a permutation check, you're going to get a runtime that's hopefully S times B, maybe as bad as S squared times B. Either way, way better than S squared times, or S factorial times B. This happens for a lot of problems. One of the easiest ways to solve a lot of interview questions is just give yourself a nice, meaty, complex example. It's part of why I push that so much on step 2. Just forget about computer science, forget about algorithms and all this other stuff. Act like you've never programmed before. Get the output. However you do it, just get the output. Then try to reverse engineer it and really think, okay, how did I do that? What I really did was I walked through every 4 characters in B. What I really did was I looked for all the A's and then look at the surrounding characters. So use that technique, get a nice big complex example, and then figure out, okay, what did I really do? This is one of the most useful and easiest techniques to apply in algorithms. Last technique I'll talk about is recursion. So there's 4 things I want to say about recursion. First thing is you have this instinct of this problem sounds recursive. A lot of people have that instinct. Great instinct, use it, don't cling to it. A lot of time, about half the time when you think this problem is recursive, it's not. So use it because it is a decent rule of thumb. You'll be right a decent number of times, but be prepared to realize maybe it's not. Second thing I want to say is you can approach recursive, you tend to implement recursion top down, but you can implement it both bottom up and top down. Or you can solve the problem both bottom up and top down. One approach might work better for one problem, one might work better for another. However, what I've found doing a lot of recursive problems, generally bottom up works better than top down. Not universally, but generally it works better just to derive the algorithm. Because people just think better, people tend to think more clearly, concretely. So, that bottom up means you have these base cases like empty set A, A, B, and then you say, okay, how can I generate all subsets of A, B, C for any of these prior answers? That's bottom up. It tends to work better. Third thing I want to say is when you're solving a problem and you think, ooh, geez, I'm going to go this way, but then I'll need to potentially backtrack. Whenever you think backtracking, think recursion. That tends to be how you implement it, and people can get really, really stuck on trying to figure out these very complex ways of backtracking, and that tends to lead to a recursive approach. So just kind of remember that instinct. Last thing, as I mentioned when I was talking about Big O, is think about repeated subproblems. When you're trying to get the runtime, draw out a call tree and look for repeated subproblems. That tends to be a useful way of getting the runtime. Okay, so those are the four major algorithm approaches I wanted to mention. Use those techniques solving problems. They are here because I've seen them come up again and again and again. So use them, practice them. When you get a problem, push yourself. It's not about do you know how to solve this problem initially. It's about can you drive through it, can you solve the problem. So really push yourself. The problems are going to be hard. Once you have an algorithm, don't just say, okay, I think I basically understand it. Now I'm going to start coding. I see it over and over again. Messes up people a lot. Take a moment to walk through your algorithm 1 or 2, 3 last times and make sure you know exactly what you're going to write. I'll interview a lot of people who 3, 4, 5 lines into the code are thinking about what their data structure should be. That's a big problem. You should know your code at the level of what all your data structures are, when exactly they change. You should basically be able to picture your code before you start writing. Because you're not going to write all of that much code. So take a moment, know exactly what you're going to write before you start writing. Rushing does not help you at all, I promise. When you start coding, your goal is not just correct code. That's one goal. But you actually want to demonstrate good coding style. So you want to write beautiful code. A couple quick things here. Some simple little handwriting things. First, try to write straight. I'm not judging your handwriting. No interviewer would generally judge your handwriting. But if you're writing and your lines are at a sharp angle, that can present some problems. It'll make your code more confusing. You're going to get confused, especially in a language like Python where white space is significant. You'll start to forget which code block each line of code is under. So try to write straight when possible. Make your life easy. Give yourself as much space as possible to write code. Usually it's the top left corner, but write wherever you have the most space. You can erase stuff on the whiteboard that you don't think you need anymore. If you need to insert new code, don't erase 3 lines of code. That'll take you a long time to rewrite. You can just use an arrow. It's fine. It's not a big deal. More important things. Think about error cases. Think about to-dos, things like that. If there's a whole bunch of little boundary checks and things like that, you may, in some cases, want to just write a to-do and explain out loud what you do, rather than writing out a whole bunch of boring boundary checks, if there's a bunch of them. Next thing, variable names. Super important. Look, we only have, as interviewers, 10, 20 lines-ish, usually, to judge you on. So one of the things we can always evaluate is variable names. It matters in the real world. So use good variable names. The problem here, of course, is that this can be verbose. If you're writing out the good variable names like number of children, handwriting is slow, right? So the compromise here is the first time, write out the long variable name. And then for each variable, write out the longer variable name. Then, after I've already written number of children, I might later on just abbreviate that as NC. You can always check with your interviewer to see that they're OK with that, but most should be. This is not pseudocode, it's just abbreviations. Language choice. Generally speaking, up to you. use whatever language you're most comfortable with. Don't try to pick a new cool functional language just to impress your interviewer. Use whatever language you're most comfortable with. There are trade-offs of every language. It honestly doesn't matter that much which language you pick. But be aware of what those trade-offs are, because there's often ways of handling that. For example, Java, known for being very verbose. A lot of people don't want to, it's very readable in that lots of people are familiar with the syntax, but a lot of people kind of shy away from it in an interview because it's very verbose. The verbosity isn't that big of a deal. You can use abbreviations. So rather than writing out something like hash map string comma integer, my hash map equals new hash map string comma integer, you might just check with your interviewer and abbreviate it as just HMS comma I, my hash map equals new dot dot dot. Literally just new dot dot dot. Your interviewer will probably be okay with that, and this allows you to avoid a lot of the verbosity. This isn't pseudocode, it's just an abbreviation. That works well for languages like Java, Objective-C, things like that. If you're coding in a language like Python, Ruby, JavaScript, people who code in that language, the issue I see a lot is that they gloss over the runtime of the different functions they call. So, I'm interviewing a Python coder, and they have a recursive method that at each level of the recursion pops off an element of the string. And they're not really thinking about it. In Python, it's like something really short, like S, or str, whatever my string is, S bracket 1 colon bracket. Pops off an element of the string. Doesn't look like a big deal. And they're not thinking about the fact that that is probably a linear time method. That means that their algorithm that maybe they thought was O of n is now actually O of n squared. So, and there's usually ways of avoiding this. Maybe they could pass in an index rather than popping off an element. But think about, so be very careful when you're using built-in methods. This actually goes absolutely just as much for Java coders and Objective-C and other languages. But Java, it's just so much more obvious that you're calling create this new string. It's much more obvious, so Java coders tend not to make the same mistake as much. Be just very aware of the runtime of the different functions you call. And you can usually just think about what they would be. If you're popping off and creating a new string, probably linear time. But again, it doesn't matter that much what language you pick. Use something that you're comfortable with. Mostly, though, it's up to you. The only exception might be that sometimes if someone's interviewing you for a very specific role, like iOS, you might be expected to code in a specific language. But this is always one of those things you can just ask. This isn't something you need to guess at. Just ask. Very important thing with coding, and a way to make your life much easier. Modularize your code. It helps in so many different ways. So a lot of people write code that looks like this. One giant method. So this is a little function that generates or walks through, I won't get into the details of it. It's called the ransom note algorithm or interview question. You can look it up. But this is an algorithm that basically processes one string, processes another string, and compares the results. This is what a lot of people write, and it's not a very good idea. First thing, instead, that you should write is that method. The overall method the first thing you write is a function that is essentially the answer to the question. And then you just pretend everything in the entire world exists, and especially the functions that you might need. So I need a function that, my process was process one string, process another string, compare the results. So that's the first thing I write, those first three function calls. From here on out, it's just filling the details. I got the skeleton of the code out, just fill in the details. Whenever I get, I go into my next function I write is the next most interesting algorithmic part. So if I need a function that converts a character to a number, like a to 0, b to 1, c to 2, then that's not something I really need to write in line. That's a very concrete chunk of code. Push it out to another function. Don't write it in line. Then I'm just filling the details. This is really nice to do. It makes your life much easier. It's much easier to kind of conceptualize all the different pieces if you're not writing out the details of one before you've written out the structure. It also demonstrates good coding style, makes it easier to test. It just makes everything so much easier. And very often your interviewer might say, and don't worry about spending your time on this one function. It's not that interesting. So modularize your code. And keep an eye out for any conceptual chunks of code. Push those off to another function. If there's like 2 steps, first I do this, then I do this, push those off to another, push those off to separate functions. If I am writing code that needs to get first the biggest element in the array, then the smallest, then I do something else with that, I would just call that as a method. Get max, get min, and then write this other part. So use modularization to your advantage. It'll not only make you demonstrate better coding style, but it'll also make your life much easier. So modularize your code. Very important thing I want to make very, very clear here is modularize your code top down, not bottom up. I'll sometimes see people who take this advice, and so the very first thing they write is this little helper method. And that's completely the wrong thing. Yes, you're modularizing, that's great, but now you're spending your time on the helper methods, the least important things. Start top down, not bottom up. This is one of the major questions people ask is, do I need to know, can I just call the built-in APIs, or do you need to write everything from scratch? If you approach your code this way, it largely avoids this issue. Assume the built-in APIs are to your, are at your disposal. You can always ask your interviewer, but assume those are at your disposal. Assume anything in the entire world you want is at your disposal. You can use whatever you want, and then just fill in the details. OK, last step, testing your code. You got to test your code. Very important. A lot of people don't do this. You got to test your code. When you do it, don't just throw in a giant test case. That, a lot of people will just take that example up on the board and throw that in as a test case immediately. And it'll work kind of, but it'll take a really long time. Instead, analyze your code. Think about what you're doing. Really, really think of, walk through line by line by line. Think, what is this doing? Talk out loud. Explain the process of your code. Double check anything that looks weird, any math, things like that. Any addition, subtraction, multiplication, division, double check those things. Those are the kind of things that cause problems. Your for loop decrements instead of increments. You did it for a reason, but double check that it's the right logic. Then start with small test cases, not big ones. Small test cases work pretty much as effectively as a large one. They're just way faster to run. Then throw in some edge cases, and then when you have time, some big test cases. 2 last things I want to say with testing. Test your code, not your algorithm. Seems obvious, and yet a lot of people don't realize what's happening. I'll see people who, their algorithms over on the left side, or their examples over on the left side, their code's on the right side, and if I were to ask them, they'd tell me they were testing their code, and yet they're not looking at their code. They're actually just walking through their example. That's validating that your algorithm works. It doesn't validate that your code does what your algorithm should be doing. So make sure you're testing your code, not your algorithm. Then, when you find a bug, don't freak out. It's totally normal. Most people I interview have bugs in their code. Again, better to not have bugs. Shoot for bug-free code. I just want to make it clear that it's not like, uh-oh, you have a bug, now you're going to get rejected. It doesn't work like that. When you have a bug, don't just rush into fixing it. Make sure your fix is the right thing. If you notice, for example, there's a piece of code that permutation problem, where you're looking through for all permutations of S. You're walking through B in windows of size S. Is this a permutation? Is this a permutation? Is this a permutation? People usually write code that looks like for int I equals 0, I less than b dot length minus s dot length, I plus plus. To walk through windows of size S and not run off the edge of B. Makes sense. Makes a lot of sense. OK. It looks right. But then they throw in some test case where b and s are the same length, and they realize, uh-oh, I run till I is less than b dot length minus s dot length. That means if b and s are the same length, that means I run until I is less than 0, and therefore my for loop never gets hit at all. Uh-oh. And they think that their bug was when b and s are the same length, and they make some initial fix in the very beginning that says, oh, OK, if b and s are the same length, do this other thing. But that wasn't their bug. Their bug was actually an off by 1 error in every single call. Regardless of the length in b and s, they have an off by 1 error. The logic actually should have been I less than b dot length minus s dot length plus 1. Easy mistake to make, really easy bug to make. I'm not that concerned if somebody makes that bug, if somebody has a bug in their code. But I am concerned if when someone finds a bug, they make the first thing that'll fix that test case and they don't think through what really caused the bug. Because that person is much more dangerous. That person gets bugs reported to them, closes the bug because they think they fixed it. They just made the code more complex and potentially introduced new bugs, and they didn't fix the actual bug. That person is much more dangerous. So when you find a bug, just don't panic. Think through, realize it's kind of normal. Think through what caused the bug and then fix that. So those are the 7 steps to solving an algorithm coding problem. Use those steps walking through the problem. So when you're going through this, actually walk through and say, oh, right, Gail said in step 7, I need to test it. Oh, right, Gail said to analyze the code, look for little things like off by 1 errors first, then go to small test cases, then edge cases, then big ones. Actually use that process. Very last thing before we wrap up, questions for your interviewer. For the most part, the major thing I'd like you to know here is you should ask your interviewer some questions. At the end of the interview, you'll get a chance to ask your interviewer questions. Have something prepared. People stress far too much about what the right questions are to ask. Ask the things you want to know, honestly. It doesn't matter that much as long as you have something to ask. Asking questions shows curiosity, shows where your interests are, your passions, things like that. So you should have some questions to ask. It doesn't matter that much what they are. That said, people always want some specific ideas. Here's what I'd say. Here's a way of just generating questions. Think about what's made you happy and unhappy in your past jobs. That's just, and that may lead you to a question to ask. So for me, I haven't been happy in jobs where I'm not given as a developer more influence over the feature set. So that's what I'm going to ask about. What kind of influence do I have? I might ask about how long it takes to launch, because I'm happier when I can launch faster. I might, ask about think about what your goals are. Ask questions around there. You can ask questions around a lot of different areas, but some of the most common things is asking about the culture and work styles, so things like, test-driven development, those kind of technical things. You can ask questions about the career path and career goals. And then you can also ask questions about technology. So that might be, which technology you use, it might be interesting technical problems, things like that. Again, have some questions ready. Ask things that ideally you actually want to know. Don't stress a ton about this, but these are just some ideas that might get you thinking about what the right things are for you to ask. All right, very last final thoughts here. Remember that all of this, everything about this process is done for a reason, and that's to identify people who would be successful at Facebook. So yes, that is about technical strength. It's also about are you the kind of person who will be successful? Can you work effectively on a team? So remember the kind of softer behavioral side as well as the technical side. Then very, very last little details. If you're ready to if you're ready for an interview, go ahead and follow up with your recruiter for next steps. And then slides are online, gail.com, click on events and search for Facebook. Or you can shoot an email, g@gail.com with the subject FB prep. And you can get a link to the slides, the handout I mentioned earlier, and some other things. So as I said, handouts online, auto response, or go to crackingthecodinginterview.com. If you want more in Big O, there's a big section, Cracking the Coding Interview, in the 6th edition for that. So you can go read that as well. And there's some exercises there. That's one of the first things I would encourage people to do is just really, really master Big O because it's so foundational. There's also a ton more problems in Cracking the Coding Interview if you're looking for more questions. You can find more in Career Cup and online as well. But do the best you can to prepare. And just remember that this is supposed to be a chance for, yes, for Facebook to evaluate you, but also for you to evaluate if you think that this would be a place where you would be effective. So do your best to prepare and walk into the interview hopefully comfortable and happy about the process you're about to go through. Thanks.